Hello, everyone. Today I'm going to talk about noise stability on the Boolean hypercube via renormalized Brownian motion. My name is Dan, and this is joint work with Ronen, Eldan, and Prasad, Raghavendra. Okay, so to start from the beginning, to define noise stability, I'll start by defining the noise operators. Throughout, we will work on the discrete cube, denoted by fancy C, and mu will be the probability measure of it. For a given noise level rho, number between 0 and 1, we define the noise operator T, which acts on functions on the cube. What it does, it takes a function, and at a point x, it generates a random point y, which is correlated with x, with correlation rho, and then integrates f over the cube with respect to that measure. Okay, here when we say that y is correlated with x, it means that it has a product measure which is correlated with x. Every bit has the same correlation with x. And this uniquely defines the measure. Now, what is noise stability? So for a Boolean function, noise stability is the correlation of f with its noisy version T of f. Okay? And if you think about Boolean functions as being some sort of voting system, each index, each entry of the hypercube says yes or no, and you aggregate all the votes to decide whether motion passes or not. Noise stability basically tells you how susceptible is your voting system to noise, right? Once you inject some noise to the system, you want to stay correlated with your original vote. So this is exactly what is measured by noise stability, and it is indeed an important concept in social choice theory, but also in Boolean analysis. Just as a nice example of an application, if you use a Boolean function to rank between 3 candidates, there is a chance you will get an irrational outcome. This is basically Arrow's theorem, and the noise stability quantifies the probability of getting an irrational outcome. So you can see that the higher noise stability you have, the better outcomes you can expect. So given that, a sensible question to ask is if we normalize a function to have 0 expectation, in which this is what we will call a balanced function, so equal chances of passing the vote or rejecting the vote, question you can ask is, among all such balanced Boolean functions, which one maximizes the noise stability? So this question has a disappointing answer, both because it's easy, the proof is easy, and because the function which turns out to maximize the noise stability is the dictator, right? Which only looks, say, at the first bit of the votes. So if you want to have a voting system which is as stable as possible, you would let just a single person make decisions. Okay, so this is a bit disappointing. Also, the proof is very short. You can simply show that monomials diagonalize the noise operator, and this is the first non-trivial eigenfunction. So to get a more democratic answer, we define the maximal influence of a Boolean function by you look at all the discrete derivative of f, basically what happens when you fix all the entries and just let the ith entry change when you take the difference. So here, this is basically the square of the discrete derivative. You integrate it over the cube, and this is the influence in direction I. The maximal influence among all directions will be the maximal influence. And then, for example, you can see that the maximal influence of a dictator is very, very large, right? It's basically 1. What happens if no single voter, no single coordinate has a large influence, right? Which would be a more democratic way to think about it. So with this notion, we can refine the question to be among all balanced Boolean function, which also have a small maximal influence, which one maximizes the noise stability, right? So another way to think about it is somehow restricting the max influence to be small forces the function to be high dimensional. It must depend on all coordinates. So maybe you can expect something interesting to happen. And indeed, this question has a much more satisfying answer, and this is a very influential result due to Mossel, Eldan, and Raghavendra from almost 20 years ago. And it is called majority is stablest. So the answer is that democracy wins, right? The majority is the most stable voting system. Let me state the result, and then I'll explain why it's called majority is stablest. Right? So among all balanced Boolean functions for which we've capped the maximal influence to be at some level kappa, the noise stability is bounded by some function of the noise, arcsine of rho, and an error term which goes to zero as kappa goes to zero, as the maximal influence goes to zero. So basically, for very small influences, you can think about this term as being the maximal stability you can achieve. And well, why is it called majority is stablest? Because if you define the majority Boolean function on n bits by simply aggregating all of the votes, checking what, which appears more, 1 or minus ones, and making just according to that, then as you take the dimension to infinity, two things happen. It's an easy computation which follows from the symmetry that the maximal influence decays to zero, which is not surprising. There is no one single influential coordinate. And on the other hand, simply from the central limit theorem, you can calculate the noise stability of majority, and this converges to 2 over pi arcsine, right? Which is exactly the quantity we have appearing here in the theorem. Maybe what we'll do now, I'll overview very quickly about the proof method, because one thing I will want to discuss today is how to improve the error term here. Right, so the way Mossel, Eldan, and Raghavendra proved the majority established theorem was to first prove an analogous result in Gaussian space, where you replace the noise operators by the Ornstein-Uhlenbeck operators, and then you can replace the majority function by an indicator of a half space. And in this case, the result was known for a long time by isoperimetry. So what they proved an invariance principle for low influence and low degree polynomials, which basically says that if you measure a polynomial in the discrete hypercube, the expectation looks exactly the same as if you would measure the same polynomial in Gaussian space. And the error term depends on two things: the degree of the polynomial and the maximal influence of the polynomial. So essentially, low degree, low influence polynomials, they behave the same in Gaussian space and in the hypercube. And of course, every function of the hypercube is a polynomial. So this is meaningful, but not every polynomial is a low degree polynomial. So the last step was to add some extra noise to the function f. So now, even if f was a high degree polynomial, by adding some noise, you essentially kill all the high degree parts and make it a low degree polynomial. And when you optimize over the amount of extra noise you need to add, you get this sub-logarithmic term. This is which is the reason for the error term. And what we did in our work, and this is what I'm going to discuss for the next 10 to 15 minutes, is that you can actually get a better error term, which is polynomial. Okay, so that's a quantitative form of the majority established theorem. So among all balanced Boolean functions with small maximal influence, majority maximizes the noise stability up to a polynomial error term. Basically, the idea is not to look at the stability itself, which is an expectation of something, rather to realize the integrand as a stochastic process and study the path of this process. Rather than we study how the process evolves in time, rather than how the expectation evolves in time. right? And the benefit is that this allows us to use stochastic analysis to bypass the invariance principle. So we don't need to add that level of noise. And for that, we introduce a new martingale embedding of mu, a new way to realize the uniform measure on the hypercube as some terminal point of a martingale, which we call a renormalized Brownian motion. And just as a remark, this method is useful for other things. We also prove a variant of a very beautiful conjecture of Kumar and Courtade about the most informative bit you can measure, but I will not discuss that at all. Okay, so let me discuss how to realize noise stability as a measurement of some process. And here is an observation. If you have any function on the discrete hypercube, the first thing we do, we extend it to a function on the solid cube, right? Because if you want to have some Brownian motion, it is a continuous object. We should work in a continuous space. How do we extend it? We extend it harmonically, right? You can think about it as solving the Dirichlet problem, but the only real thing to think about is this is a byproduct of the definition, okay? For a point in the cube, f of rho is the noise level of x, simply equals the noisy version of x, right? So instead of integrating some random vector over the entire cube, it's enough to evaluate a single function, the harmonic extension, inside the solid cube. Now, this allows us to write the noise stability in a new form, right? If we take mu rho to be uniform on a small hypercube, dilated hypercube, then simply because we have the identity which relates the harmonic extension to the noise operator, we can rewrite the noise stability in the following form. Now, one fact about the noise operator is that it is self-adjoint. So instead of applying raw noise to one copy of f, you can apply square root rho to two copies of f, which is what we have here. But then we're basically just integrating f against itself, or rather the harmonic extension of f against itself on a smaller hypercube, which is exactly dilated by a square root rho factor. Right? So we realize the noise stability of f as an L2 norm of f with respect to some other measure, which is not the uniform measure on the discrete hypercube, but on a dilated hypercube. So we can try to generalize that. Right? If we now take any measure which is supported on -1, 1, we can think about its product, which is supported on -1, 1 to the n. It's an n-dimensional measure. And we can define the noise stability of rho, so the noise stability of the measure nu of f as just the L2 norm of f with respect to the product measure. And turns out that our not so complicated computation shows that this is exactly equivalent to the original noise stability, where the noise level is simply given by the variance of mu. Okay, so this just follows from an L2 decomposition. But now we have a strategy, right? Because suppose we can find some stochastic process whose law will denote by nu t, and suppose that at time 0, the process has variance 0, and at time 1, it has variance 1. Right? The only possibility for it to have variance 1 if it is supported just on the two endpoints, -1 and 1. And at every intermediate time, the variance will interpolate between 0 and 1. Then that process will encode, if we apply f to the process, it will encode the noise stability for any noise level, right? Because we can simply take an L2 norm with respect to the process. And then what we'll need to do, we'll need to compare it to the exact same process when we apply the majority function. Okay, so that's our goal, to find the process such that we can compare any function to majority. So here is the process we used. We call it a renormalized Brownian motion. Hopefully it will be understandable why. So it is an Ito process driven by a Brownian motion. it's a martingale. And for balance function, it will always start from the origin. And it evolves in the following form. We multiply by Brownian motion by some matrix, sigma t. Sigma t is a diagonal matrix, which basically means that xt will have independent coordinates. And what we multiply each coordinate by is the following quantity. It's the square root of 1 minus xt times x plus 1 plus xt. And as according to our goal, we can define nu t as the law of xt, or at least the first coordinate of xt, then it's a product measure. So here are some basic facts. You can calculate the variance of nu t from e to the lemma, turns to equal 1 minus exponential of negative t. So you can see that at time 0, it's 0, and at time 1 at 1, it's 1, and every intermediate time, it is some value between 0 and 1. Well, if you define yt to be the conditional measure of the endpoint with respect to the current place, then xt is just the expectation of yt, which is not surprising, right? Because xt is a martingale. This simply expresses the martingale property. But you can also calculate the covariance matrix of yt, and it turns out that sigma t is exactly the covariance matrix. So basically, every point, we check what is the covariance we have left until the terminal point for the martingale, and this is what we normalize the Brownian motion by. Okay. So what we do with this process, for a given Boolean function, we define the following process. Apply f to xt. This is a real valued process now. X is a martingale. F is an harmonic extension now of a Boolean function. So it is an harmonic function. And an harmonic function of a martingale is also a martingale, right? So we've obtained a new martingale nt, which means that we can evaluate the L2 norm of f with respect to the measure of xt with respect to nu t simply as the quadratic variation of the process on one hand, or just the square of the process when it starts from 1, and it also encodes for the noise stability of f. Right? So what the proof does now, it constructs a different process, a different martingale, empty, which encodes the noise stability of majority. And now once we have two martingales, NT and empty, we couple them together to, well, ideally, get an almost sure equality of the form that the quadratic variation of one martingale is smaller than the quadratic variation of martingale, or in simpler terms, the square of one is always smaller than the square of the other, right? Because then when you integrate, when you take expectations, this inequality is maintained. So everything relies on finding this, on finding such a coupling, right? So maybe to recap on what we have, we wanted to prove that the majority is stateless, that the noise stability of f is smaller than basically the limit of the noise stability of majority plus some error term. And the main ingredients we have a martingale NT to represent the noise stability of f. We will need another martingale MT to represent the noise stability of majority, or rather its limit, which is basically this arcsine function. And what we will prove that the quadratic variation of m satisfies a differential equality, and that the quadratic variation of n satisfies, well, the same thing almost as an inequality. This will allow us to compare between those, or rather to construct a coupling which will compare between the two processes. So let me explain now how to construct the process, or how we constructed the process M. Right? Because there are infinitely many martingale, there are infinitely many processes which satisfy this relation. You can even take M to be deterministic if this is what you care about. But we want a martingale whose path will interact well with the process nt, basically the Boolean function f applied to xt. So the easiest thing you could do is you could apply majority to the process xn. But this is somehow not such a canonical choice because majority is different in every dimension. And we want really a limiting object. Right? Otherwise, we will need to account for the error term of majority with respect to arc sign. So instead, because somehow majority was proven by a reduction to Gaussian space, we will instead take a Gaussian process which encodes for majority. And this takes us back to the isoperimetry, which was already appeared in the previous work. Right? So if phi is the cumulative distribution function of the Gaussian, and the derivative of phi is basically the Gaussian density, if we apply the density to the inverse of the CDF, this is what is called the Gaussian isoperimetry profile. Right? It basically measures the surface area of hyperplanes. And what we define the martingale by, we define it to satisfy the following stochastic differential equation. Right? So again, it is a Brownian motion, but it is renormalized according to the Gaussian isoperimetric profile. And once you defined it, the calculation shows that it exactly encodes the noise stability of majority in the limit. So this thing equals to arc sign of some quantity. And just by definition, it satisfies a differential equality, right? The derivative is given by the isoperimetric profile squared. What we prove for the original process, which is basically Boolean function with a small maximal influence, is that any such function, when you apply to the process xt, satisfies almost the same differential expression with an inequality. It's always smaller than it. So you can expect this quantity to evolve at a slower rate than this quantity, but there is some error term. But the error term is polynomial. That way, when you integrate everything, you will only get a polynomial error. So, thank you for listening.